Now, when we talk about magnets and magnetism and magnetic field, we have to know what's the magnet. The magnet is a piece of metal that attracts ferrous materials to its poles. Okay? No problem. Okay. Now, when we say that, that means we have something called ferrous materials. What are the materials that the magnet attract to it, and what are the ferrous materials? We have 4 different ferrous materials. Who can tell me what are they?
Cobalt, nickel, and iron.
Exactly. Iron, cobalt, nickel, and what? Steel. The most important materials here are what? Are iron and steel. Why iron? Because iron is temporarily magnetized. So I can use it, okay, to make electromagnet magnetized. So to make electromagnet, while steel, it's what? Steel is what? Permanently magnetized. Permanently magnetized. To make magnet. To make magnet by them, magnets. That's the first thing. Second thing, we have something called poles, and we have 2 poles here. One we called north, and the other we call it what? South. Why they call it north and south poles? Why do they call it north and south poles? Because we know that the Earth is a huge magnet. The Earth, it's a huge magnet. This is the Earth. And if we hang a magnet freely close to one side of it, of the Earth, we can see that this magnet, okay, it will attract to the north of the Earth or attract to the south of the Earth. That means the Earth is a huge magnet, that its south magnetic pole is located in the north geographically, and its north magnetic pole, okay, it's located where? In the south geographically. Okay, so the Earth is a huge magnet that flip upside down north and south in the opposite direction. So we don't know that unless, okay, we didn't know that as a human being unless the last few hundred years. Okay, so how can we make a magnet, or how we can demagnetize a magnet? That's very important, because we know that any magnet, it can have all the magnets, they can have different shapes. For example, a straight road, for example, this is north, this is south, or a horseshoe. Okay, one is north and one is south. Okay, so if I break one magnet, if I break one of these magnets, okay, what will happen? It becomes 2 magnets. I can't find north pole by itself or south by itself. So the north, as you can see, there's magnetic field lines coming out from the north, and they are seeking to go where? To the south. That's outside what? The magnet. But actually inside the magnet, the dipoles, they are aligned to make this lines are continuous line like this. So that's what the lines from the south like this. Okay, forget my drawing, they are not that accurate. Okay, like this. And the same thing, okay, for the north and the south for horseshoe, it's always the magnetic field lines come out from the north, go where? To the south. And as you can see, I tried to draw these as parallel lines. That means we are talking about uniform magnetic field in the horseshoe and always going from the north to where? To the south. Okay. If we break a magnet, it will become two magnets. Okay. So one of the questions that we have to know it, how to make a magnet and how to demagnetize what? A magnet. Okay. First question, how to make a magnet. Okay, how scientists know that it comes from the north? They assume that they make like what we assume about the positive and the negative. They have conventional current that come out from the north, from the positive to the negative. They assume that the magnetic field lines coming out from the positive, the north, and go to where? To the south. How we can a magnet? Magnet can be done, okay, by three different methods. Number one, by stroking, not by rubbing, by stroking. And what that means by stroking? Now I can bring a steel bar because it's temporarily magnetized or permanently magnetized. Thank you. I can bring a steel bar and I can bring a magnet, okay, and this magnet I will stroke it above the other steel bar in this way. So as I stroke it, this is north, this is south. As I keep stroking it in one direction, like this, from here and go up and repeat this again, I keep move it on the steel bar several times, hundreds of times. Eventually, after a while, this steel bar becomes what? A magnet. This steel bar becomes a magnet. And as the north is going in this direction, it attracts all the south and put it where? Put it here. So this side becomes south, since this side was north, and the other side will become what? North by this movement. How can I make this steel bar becomes a stronger magnet? And how can we make it stronger? To make this magnet stronger, thank you, Marwan. No. What do I need to do? I need to make more strokes. Bravo. More strokes. That's number one. More strokes. Number two, okay, use a stronger magnet, not a small magnet, a stronger magnet, bigger magnet. Use a stronger magnet. This is the first method to make a magnet. The second method to make a magnet by induction. What do I mean by induction? If I bring, for example, iron fillings, okay, iron needles or iron pieces of iron, okay, there is no empty space. خلاص مش مشكلة. Okay, by induction, what I will do, for example, هاي خلصنا هذا رسمه. هلا جبنا المagnet, okay, and I bring some paper clips. These paper clips are made by what? Steel. You can see that they join each other. They are connected and make a chain. Okay, so if this side is north and this side is south, that means all these paper clips that made by steel, this becomes south and this becomes north. It's magnetized by induction, and this side becomes south and this side becomes north, and etc. North, south, north. So if I release the first one, the rest of the paper clips will stick a little bit, okay? Why? Because they are made by steel. But if I use iron nails, okay, and I put them towards each other like this, as you can see, they move away from each other. Why they move away from each other? Because they will be magnetized. For example, this side is north, this side is north, and the other side is south, south, south with south. They will what? Repel, as you know. So whenever I put iron, okay, it will be joined to it like this. But whenever I drop the first one, I release it, all the chain will fall down because they are temporary what magnetized. This is north, this is south, this is north, this is south, etc. This is number 2. If you please take a screenshot. Okay, let's take a screenshot for the beginning here, the first one. And take another screenshot here for the other method. Okay, I want to erase and put the third method. There's no enough space, okay, unfortunately. The third method, what is it? The third method is by what? By direct electricity, direct current, by solenoid. Solenoid has DC, direct current. So what do I have? I bring a copper wire and I make it turns, okay, like this, several turns, okay, around a card piece of paper. And I have a switch with what? With a battery. And I put inside this cardboard, okay, the core that I wanted. I can put steel or I can put iron inside. So since there is a current, and this current is moving in one direction, that means one of these sides, as we're going to study later on, becomes north and one other becomes south. So in the core, I can put one of two things, steel to be a permanent magnet, or I can put iron to be an electromagnet. And as we are going to study, okay, whenever the number of turns here is more, whenever the current here is greater, that means this magnet will be stronger. To have a stronger magnetic field, we need more turns, and also we need what? More current. More current. These are the three different ways to make a magnet. The opposite question, how can we demagnetize a magnet? How to demagnetize a magnet? Who can tell me how to demagnetize a magnet? On the chat, how can we demagnetize a magnet? We have three different methods. Okay, yes, thank you. Number one, heating it until it becomes red, by heating until it is red. Okay, that's number one. Red, it's very hot. Okay, number one. Number two, by hammering it several times. Thank you, bravo. By hammering it. I know. You can write on your notebook. If you don't have enough space, you can write on your notebook. Okay, by hammering it many times. And number three, by a solenoid, by putting it inside a solenoid, has not direct current, alternating current, has alternating current. Instead of having a battery, we have an AC source, okay? And do one of the two things. remove it slowly, remove it slowly. We take it out slowly from this solenoid, slowly, okay? Or what? Reduce the current slowly. Reduce the AC slowly. The AC slowly. Okay? That's it. Okay? So this is the first page here. Okay? That's how we can make a magnet. Okay? And this is how we can demagnetize a magnet. Okay? Now, we have multiple choice questions as usual. These multiple choice questions are what? Are your homework. Okay? For next time. Can I go back? This one? Okay. We have multiple choice questions as usual. You have to do them as homework. Okay. Then go to page number 4, if you please. In page number 4, what they ask? Magnetic field is not only caused by a magnet, permanent magnet. I can bring a magnetic field from our phones. Why? Because there is a current passed through a certain what? Solenoid. So that means when there is a current, this current can make what? A magnetic field. How does this happen? Let's start to talk about normal current by straight line wire, how the magnetic field is produced. Then we talk about circular coils or what? Solenoid. For example, the magnetic field caused by electric current, first example, in the straight line wire. If I have a straight line wire, you can see that as the current passes, it will produces what? Magnetic field. And how this magnetic field will looks like? They looks like what? Ripples. They looks like waves, but they have increasing distance. Look, this is here, it's close, here farther a little bit, and much farther, etc. So as we go away from this wire that has this current, the magnetic field gets what? Weaker. Bravo. صح. So straight line wire, the magnetic field lines in the test don't write like this. MF. I'm going to write a lot the word magnetic field, magnetic field, magnetic field. So I'll write it MF. Okay. So I want from you, don't in the exam write MF, like kinetic energy, KE. Kinetic energy is accepted, KE. But magnetic field is between you and B. Okay, so we cannot continue writing a lot of the word magnetic field, magnetic field, magnetic field. So the magnetic field around the wire is like ripples, circles, circles that has the same center, that has the same center, which is the wire, which is the wire. With farther distance, farther distance. Okay. How we can indicate the direction of the magnetic field by using something called what? Grip right hand rule. By using what? Grip right hand rule. What's the grip right hand rule? For example, this is the wire that has the current is out of the page, out of the paper. I'll put my thumb. I'm talking about right hand. So if you are writing with your right, put your pen away and use your right hand. Okay. Don't keep holding your pen by your hands, right or left, okay? Because you will get confused. Some students, they start using their left hand, not the right hand. So there's a wire that has a current. I will put the thumb in the same direction as the current. I close the fingers as the direction of what? Of the magnetic field lines. Okay, and as you can see here, the magnetic field lines, they are moving what? Anticlockwise also here. So if the current is not going upward, if the current is going downwards, that means the magnetic field, it will be the same, but it will be reversed. Instead of being clockwise, it will be anticlockwise in the opposite what? Direction. Okay, so by using grip right hand rule, what the grip right hand rule says: thumb in the same direction as the current, closing the fingers, closing the fingers is the direction of the magnetic field. Okay, take screenshot here. Let's move on. Question: how can we make the magnetic field at a point increases around the current, okay, in a straight line way? How we can make the magnetic field at this point stronger? What we need to do? How can we make the magnetic field here stronger? What do we need to do? Send me on the chat, or if you want to turn on your microphone, it's my pleasure. Bravo, Marwan. Another answer. Exactly, Muhammad. Same answer as Marwan, but different way. A third answer. Okay, we can increase the current or increase the voltage. This is one accepted answer. So number one, more current, or you can say potential difference, more voltage. Okay. Number two, less separation distance, less separation distance to the wire. Yeah, whenever the wire is closer, yani, instead of being the wire like here, I put the wire here closer. That means it will be stronger. So less separation distance to the wire. Okay, let's move on. Circular coil. They didn't ask about it that much, but maybe they ask about it as multiple choice question. What do we have in circular coil? We have magnetic field lines that concentrate at the center of the circular coil, and it's uniform because they are parallel lines here at this region. Okay, in the center they have uniform magnetic field since they are parallel lines. So what am I going to say here? At the center, the magnetic field is what? Uniform and perpendicular to the what? To the plane of the circle, or to the coil, and perpendicular to the coil. Now, here, to indicate the direction of the magnetic field, I use what? Grip right hand rule. I said that the thumb in the same direction as the current. But here, I will not do the same. I will say that the closing the fingers are in the same direction as the what? As the current, and the thumb will indicate the direction of what? Of the magnetic field. So I'm going to use also grip right hand rule, but in another way. Grip right hand rule. What does it say? Okay, grip right hand rule. This is R. Okay, closing fingers in the same direction as the current. The thumb shows the direction of the magnetic field. The thumb shows the direction of the magnetic field. Good. Let's move on. How can we make the magnetic field lines at the center of the circular coil increase? How can we make the magnetic field here stronger? على فكرة الانسرز they keep repeating each other. شو كتبنا هون؟ More current, that's accepted answer. شو قصدنا بال separation distance? Here what we are going to say? Instead of
diameter.
exactly less diameter. Bravo. So less radius or less diameter. Excellent. So okay, we can put three different answers, and the third answer, no one mentioned it in the chat now. So more current, that's number one. Number two, less radius or less diameter. Less
Third
radius.
one is something related to circumference.
It's less radius relative to circumference. Number three, instead it's a coil. It's a coil. Instead of having one wire, I will have what? Increase the number of turns of the coil, right? More turns of the coil. More turns of the coil. Okay. So we talk about straight line wire. We talk about circular coil. Now we'll talk about solenoid, that the coil has a spiral shape, like some of your notebooks, that there's a wire that hold the papers. It has a spiral shape. That's called what? A solenoid, like springy shape. Okay. So what will be the magnetic field looks like in or around the solenoid or springy shape coil? The magnetic field inside are parallel. You can write uniform. And outside it looks like a magnet. A magnet with north and south, with north and south poles. How we can indicate the direction of the magnetic field, which one is the north and which one is the south? Also by using what? Grip right hand rule. In this situation, for example, this is the coil. Look to the direction of the current. The current is rotating in this direction, the part that I can see it. It's going upwards. So I put my hand, the fingers going up. Okay, my thumb will indicate the direction of what? Of the magnetic field. So as this one, these are my closed fingers, okay, in the same direction as the current. My thumb will show me the direction of the north of what? Of the magnetic field inside the solenoid. Grip right hand rule. Closing fingers. Same direction as the current. The result that the thumb will show me the direction of the north of the magnetic field. Okay, or the right rule that I heard of different from this. Okay, tell me about the right hand rule. That you means the grip, the Fleming's right hand rule, this one? No, wait a moment. لسه احنا لسه من بداية الماجنت. هذا أول إشي. لسه في كمان هيك وفي كمان هيك. لسه مطولة. Yes, لسه مطولة. Fleming's right and Fleming's left hand rule. لسه. We have a lot of things that we have to talk about. Okay. Look here يا شباب. For example, we have a solenoid. Let me draw a picture for you, and you will tell me, okay, in which direction is the north and this direction is the south. This is a cardboard that has rotation circles like this. and I bring, still we have a lot to headache, yes. Okay, we have a coil like this, like let's rotate like this. Okay, and I connect it to what? To a battery in this way. Now, as we know that the current is going from where? From the positive to where? To the negative. So the current is coming out from the positive, go to the battery. In which direction does the current flows? In the part that I can see, to the left or to the right? To where? To the left. So I put my fingers in the same direction to the left on the paper, like I'm trying to hold it, okay? In the same direction as the current. My thumb is going where? Downwards. That means this side becomes north and this side becomes what? South. Okay? Good. Write these down, take a screenshot. You have to copy all this information on your worksheet after you finish, okay? Then what they said here. Question 3. How can we make the magnetic field at the center of the solenoid increase? Who can tell me how can we put a stronger make a stronger magnetic field at the center of the solenoid? Yes, it's similar to the one previous one. Yes, more current, less radius, more turns in the coil. Yes, bravo, excellent. So number 1, more current. Number 2, less radius or smaller area of the solenoid. Smaller area of the solenoid. When I say the area here, cross-section areas. Okay. And number 3, more turns for the coil. More turns of the coil of the solenoid per unit length. Per unit length. What do I mean by per unit length? That means maybe I don't increase the number of turns, but instead of make them these 10 turns or 20 turns, they have this distance, I put them close to each other. So these turns will be looks like this. Okay, in this area, instead of having all this length, it's smaller length. So I can make them what? Much concentration. Okay. Tamam? Any question? Okay, let's move on. There's something called electromagnetic induction. Okay, let me show you something. Okay, here in this lesson, what do we have? First, we talk about the magnet by itself. The magnet that produce magnetic field that's come out from north to south. Then we talk about wires that when there is a current pass through them, they produce what? A magnetic field. Now let's say the opposite. Can the magnetic field produces current? Can we reverse this? Instead of having current that produce magnetic field, can the magnetic field produce a current? Yes, that's called electromagnetic induction, our title now. To make electromagnetic induction, I need to move the wire. I need to keep rotating it, to keep cutting the magnetic field lines. Okay, that's how the windmills they produce energy by what by generator. Yes, شكرا يا محمد صح. Okay. So again, we have magnet by itself. Current produces magnet. Then magnet produces current by motion, by cutting magnetic field lines. Can we make motion from magnet? Yes, we can bring a magnet and we can put a wire that has current inside this magnetic field lines, and there will be a perpendicular force that moves this wire like something called electric motor, like Tesla car, like the fan, like the dynamo that has sorry, the water pump that you use it to push the water upwards. Now this has a coil that has a magnet also. When there is a current pass through this coil inside this magnet, it starts to what, to move. All these, as you can see, they are relative. So we talk about the magnet, we talk about wires, current make a magnet, then magnet makes a current by cutting, by motion, then magnet by cutting makes what, induced current, or current by motion, sorry, current inside magnet make what, motion. All these lessons, they are vice versa. You have to understand them. Yes. So we'll talk about generator, AC generator, and we'll talk about DC motor. Now here, electromagnetic induction, we are talking about what, AC generator. So what's the meaning of electromagnetic induction? When the magnetic field lines are being cut by a conductor, and there's two ways to do that. Okay, when it's being cut by a conductor, the electrons inside it, they start to move. And as they move, that means there is a potential difference. There's induced EMF. There's one side is positive and one side is negative, and the current will flows between them. Okay, so that's called what, electromagnetic induction. So the electromagnetic induction, when a conductor cuts the magnetic field lines, there's an induced EMF, like a battery. Yes, EMF. There's an induced EMF across it. مين هو هذا الإت؟ الكوندكتور. Making induced current flows. Making induced current flows through it. Current flows through it. it اللي هو الكوندكتور. Okay. So again, this electromagnetic induction, the application of the AC generator, can happen by two different ways. There's two ways to produce an induced current or electromagnetic induction. First way, by moving a magnet inside a solenoid, and this solenoid has an induced current, or by move the wire, okay, inside what, a magnet. So we can move the magnet or we can move the wire. In both ways, we have relative motion to cut magnetic field lines. If there is cutting of the magnetic field lines, that means there will be a produce of induced EMF. Okay, let's talk about the first one. Okay, for example, I move the magnet here with a slow speed inside the solenoid. As I move the magnet slowly inside the solenoid, look what happens. There is a small current, a small reading. It's not zero, it's a little bit shifting to the right. But as I move the magnet faster, I'm cutting the magnetic field lines more. شو يعني أستاذ magnetic field lines؟ شو اللي بتخبصه يا أستاذ؟ Look here, I'm talking about magnetic field lines that come out from the north, go where? To the south. When the magnet is far here, the number of magnetic field lines inside the solenoid may be one, like this one. But as I move it closer, all these coils, they cut this one, this one, this one, this one. So as I'm cutting the magnetic field lines, okay, that means there will be what? Movement of the electrons inside. For example, let's imagine a huge spider web in one of the doors, okay, for empty houses. If I cut one string, okay, of this spider web, the spider will get afraid and move away. If I cut two strings, it will move much farther. If I cut the whole web, it will jump. The same thing, when I move the wire or the magnet and I cut by this wire magnetic field lines, each magnetic field lines is being cut, one electron or one spider, one electron is moving from one side to another. That means I'm talking about a huge number of electrons, they keep moving as I keep cutting the magnetic field lines. So that's why when I move the magnet faster, there will be a higher reading. When I stop the magnet for an instant, whenever it stops, the reading becomes how much? Zero, there is no reading. But as I move the magnet in the opposite direction, the reading is exists, but where? In the opposite direction. Why? Because instead of cutting downwards, for example, I'm cutting upwards. Instead of moving inward, I'm moving what? Outward. So, and whenever the speed is faster, the induced current or the induced voltage, it will be what? Higher. Okay? So from these pictures, what do we realize? We realize two things. What are these two things? Maybe it's AC if I keep moving the magnet in and out. Yes, like it's AC generator. Yes. What do we realize here? As the magnet is moving faster, the induced EMF, it will be what? Higher or it will be lower? As I move the magnetic field line, it will be higher. As the magnet faster, the cutting of magnetic field lines will be higher. Good. As I reverse the direction of the motion, what will happen to the induced current or induced voltage? It will be what also? It will be reversed, right? So, first point here, faster motion means what? Means higher EMF. Number two, reversing motion, reversing motion, reverse direction of induced EMF, reverse induced EMF. Write these down if you please. Next, now how can we indicate the direction of what? Of the current. Now maybe they bring one multiple choice question or one question about this, or maybe they don't bring any question about it at all. So we have to focus about the idea to get this 1 mark, or okay, do not waste a lot of time to understand it. Only a small idea. Now you understand it, okay, and don't do a lot of things thinking about how you understand or you don't understand, because it's easy. Look what's happened. For example, I bring a magnet. This is north, this is south. This is north and this is south. And I do not move it. The speed is zero. The speed is what? Is zero. Is there is cutting of magnetic field lines? When the magnet is at rest, does this solenoid cut the magnetic field lines? Thank you, Muhammad. No, it doesn't. So is there will be an induced EMF? Shukran, Adham. No, there will be no induced EMF. So how much the reading of this voltmeter or this ammeter it will be? It will be how much? It will be zero. Excellent. It will be what? Zero. But in nature, if you, Adham, or you, Muhammad, are in front of me, and I'm trying to what? Suddenly to push you. Okay, I make a surprise for you. I want to push you. What you will do by your body? You will move your body forward a little bit. You want to resist my push, but you will not resist it. You will move away. Okay, so you try to push, okay, to resist it. This is what happened to the magnet, and this is what happened to the nature. For example, if this north and this south, and we move the magnet closer to this solenoid. Now we know that there will be a current here, and this current will produce a magnetic field opposes the increase of this magnetic field. How do I oppose it? This side becomes north or south to oppose the increase of the north, or make the north getting not closer that much. This side, it will be north or south. This side, it will be north. North and north repulsion. It seems that they will repel, but they don't repel each other. The north keep moving. And this side will be what? South. So by using grip right hand rule, if this side is the north, that means the current that I can see it by my closing fingers, my right hand, okay? It will be in which direction? It will be what? Upwards. That means it will be up from this side, down from the other side. That means the pointer will go to the right like this. Again, if I move the magnet, this is the north and this is the south, and I move the magnet away from the solenoid. Like I'm trying the adham, okay? I'm trying to what? To hold your shirt and pull you towards me. What you will do, your body will move backward a little bit. You resist my pulling. How this solenoid resists the pulling of the north? This side becomes what? South, because south and north, they will attract. It seems that they will attract, but it doesn't. Okay? That means if this side is south, the other side will be what? Will be north. So by using grip right hand rule, this is the side is north. So that means the current from the side that I can see it, it's going where? It's going downwards. Yes, it's going down. That means this side is going down, this side is going up. That means the pointer is going where? In the opposite direction. Opposite to this one. This north getting closer, so the pointer go to the right. This is the north going away. That means the pointer go to the other direction. Okay? Again, let's imagine that I'm not talking about north, I'm talking about south. And this is the north. And I'm getting closer the north to this solenoid. That means this side of the solenoid will become north or south. South is getting closer. That means this side becomes south. Yes, exactly. And the other side becomes what? North. Use your grip right hand rule. Imagine this is the solenoid that you hold it. This is the north. When you close your fingers, that means the current that you can see it is going where? By closing the fingers, is going where? It's going down. That means the pointer will go to where? To the right. أستاذ خليني أحفظها لما يقرب النورث بروح يمين لما يبعد النورث بروح شمال. Don't do that. Don't memorize it like this, because maybe they will reverse the turns as this question. Instead of making the turns anti-clockwise, they make the turns clockwise of the solenoid. So you don't know. Okay. So for example, let's repeat this one. Okay. If this is north and this is south, and I move the magnet away. I move the magnet what? Away. That makes this side is what? South, like this one. And this side is north because I will attract it. I want to resist its motion. I don't want to move it away or even to move closer like here. So by using grip right hand rule, this side is north and grip right hand rule, that means the current is going down like this. So the pointer will go to the right. Look, these two cases are exactly the same, but the turns are reversed. Instead of having clockwise, they are what? Anti-clockwise. Okay. Last example عشان ايش اتاكد ان امورنا تمام. If you have any question you can ask me. Okay. مين من زمان ما سمعنا صوته. Let's say ايش سلمى. Selma, you are here. Okay. This magnet. Do you want north or south to ايش close to the solenoid? Pick. North ولا south? Selma, يلا. Tell me. Anyone. Okay, north. That means this side is south. طيب, this north is getting closer or getting away يا سلمى? What do you want? Closer or away? Okay, away. This is the direction of motion. That means, what will happen to this side as the north is moving away? What will happen to this side, ya Salma? North or south? Because it's moving away. It will be south. If it moves closer, it will be repulsion. If it moves away, it will be attraction. So it will be south. That means this side becomes what? North. By using grip right hand rule, this is the north and this is the solenoid. I'm holding it by my hand. I can see that the current that I am seeing it is going where? Is going down. So the pointer here is going to the right. Usually they don't ask questions about in which direction is the current. Rarely. But we have to know this information, okay? Good. Can we take a break? No, we are not going to take a break. It's less than 40 minutes and we are going to finish the class. يلا بسرعة. We are going to finish. It's only 11 weeks to your external. We have to finish the whole thing, okay? I can't keep giving you breaks because I was absent for several times, so I'm late a little bit, okay? طيب. Now, as usual, okay, we have a question here. How can we make the reading of the galvanometer or the voltmeter be higher? كيف بدنا نخلي reading of these okay, higher? Who can tell me what I need to do? What I need to do to make the reading here of the induced current? Well, I didn't hear what?
Higher voltage.
How can I make it higher voltage? There is no battery here. I need to induce voltage. How can I make it higher voltage? Which Italian scientist? Galileo?
No, Galvani. That guy
Galvanometer.
who
Galvano. Yeah, galvanometer. Yes. Use a stronger magnet. Bravo. One. Move it faster. Bravo. Move it faster. Okay. Move the magnet faster. Bravo. What about the turns here? Exactly. More turns. Okay. شايفين كيف? No, the answer. إذن first one, move the magnet faster. Okay. Number two, use a stronger magnet. Whenever the magnet is stronger, that means there is more magnetic field lines, so it will be more cut. Use a stronger magnet. Number three, more turns for the solenoid. More turns for the solenoid. Now, how can we make the reading of the voltmeter is reversed? Instead of make it to the right, becomes to the left. What do we have answers here? How we can make the reading of the voltmeter or the galvanometer or the ammeter be reversed? Exactly, switch the direction of motion. Instead of getting closer, I will move it what? Away. Bravo, that's one answer. Or reverse the polarity of the magnet. That means instead of using north, I will use the south. But if I do both, if I switch the magnet and switch the direction of motion, that means negative, negative. So the answer, it will be the same. So I can't do both. I will do one of them. So reverse the direction of motion or what? Switch the magnetic pole. Switch the magnetic pole. Okay. برافو عليكم. والله فنانين ما شاء الله عليكم. إبراهيم ومروان يا سلام. وأدهم ومحمد ما شاء الله كلهم بيجاوبوا. حتى الصبايا. طيب. Now that's how can we move the magnet to the solenoid. This is one of the method. Now let's do the opposite. Move the solenoid. Okay, move the wire inside the magnetic field. Move the wire inside the magnetic field. Let me remind you about something. In paper 4, the greatest topic that they bring a lot of questions about it is general physics. The second most important topic here is electricity and magnetism. They bring 3 questions or rarely 4 questions. These 3 questions, usually one question about electrostatic or electric circuits, one question about electric circuits and electric components or parallel and series, one question about logic gates or electrical components with what? With magnetism, or a whole question with magnets. So not necessarily every year they bring question about magnets. on magnetism and this topic. This lesson talks about a lot of things, a lot of ideas about how to make a magnet, how to magnetize a magnet, how can we make electromagnetic induction, what about the generator, what about later on transformers, what about magnetic force, what about how we can explain the DC motor, how does it work. All these, they have different lessons. Okay, each lesson, maybe they bring a question about one or two ideas, maybe they don't bring it at all. Okay, good. Okay, so let's say that, let's talk about how we can move a conductor inside what? A magnet. For example, this wire, as you can see with the arrows, I move it between these two magnetic poles, and we have millions of magnetic field lines that are unseen, that they are going from north to what? To south. So as this wire is moving between these magnetic poles, it cuts the magnetic field lines. It cuts what? The magnetic field lines. In the mark scheme, they change. There's another word, change the magnetic flux. We will talk about it later. But it's the same as cutting the magnetic field lines. So as the magnetic field lines being cut by the movement wire, there will be a potential difference between its edges. That means one of the side becomes positive and one of the side becomes what? Negative. So if I connect these to a voltmeter or complete circuit, that means there will be a current pass through the circuit from the positive to the negative. Okay, so what do they ask here? Let's see, what do they ask? Okay, first we have to write this down as a wire, is moved inside magnetic field to cut its lines in a perpendicular way What do I mean by perpendicular way? Look here. Look to my hand here. If I move the wire like this, and this are the magnetic field lines. This is north and there is south here, and the magnetic field lines going from north to south. If I move the wire like this, I don't cut the magnetic field lines. If I move the wire like this, I don't cut the magnetic field lines. Only if I move the wire like this or like this, I'm cutting it. If I move it sideways like this with an angle, the rate of cutting magnetic field lines, it will not be as fast as this one, this way. So here in perpendicular way, like this or like this, they are perpendicular, the motion with the magnetic field lines. I'm talking about maximum cutting of magnetic field lines, okay, if they are perpendicular, okay. As the wire is moved inside magnetic field cuts is okay in perpendicular way, an induced EMF voltage, yes, an induced EMF is produced across it. Making an induced current to flow if there is a circuit, if there is a closed circuit. Good. Okay. How can we know the direction of the current? In which direction does the current will be? Okay. Now we are going to use something called what? Fleming's right-hand rule. The Fleming's right-hand rule, like this or like this, it doesn't matter, or American way like this, doesn't matter. You have to indicate the direction. Okay. We are talking about three different dimensions, X, Y, and Z. Okay. This one and this one, they are perpendicular. This one and this one, they are perpendicular. All these three fingers, they are perpendicular to each other. Okay. We have three fingers. One they call first finger, one they call second finger, this one, and what we call thumb, as you know. So first field. So when we talk about first finger, we're talking about magnetic field. When we talk about second finger, we're talking about current, second current. When we talk about thumb, motion, we are talking about motion. The thumb means the motion, the thrust. Okay, so let's see this example. Here we have a 3D dimension picture. As you can see, we have 3-dimension picture. I'll repeat it as 2-dimension picture here. We have south, we have what? North. The question can be 3-dimension in the exam, or can be 2-dimension like this one. And this is the wire. As you can see, this is the wire. And this wire is moving up, cutting the magnetic field lines between the north and the south. So we have magnetic field lines from north to south. We have this wire. Okay, this is a cross-section area of this wire, and this wire is moving in this direction like this. So this is the motion, V, and this is the magnetic field from north to south, MF. Now, in which direction is the current? I'm looking from here. This is my eye. عشان تطلع two dimensions. In which direction is the current? We will use our what? Our right-hand rule, Fleming's right-hand rule. And this one, in this question, do not twist your whole arm. Rotate the paper that has the question, rotate it to make it easier for your hand. So first finger, as I told you, it's magnetic field. It's always from north to south, like this. And the thumb is the direction of the motion, is going where? Upward. Look, where's the direction of the current? It's out of the page, coming to me. Not into the page, out of the page, coming to P. So this is the direction of the first finger from north to south. This is the direction of the current. So the direction of the current, it will be out of the page, like here. It's going in this direction. Okay, and that's why the pointer go to the right. So here, okay, as we study, okay, before, we have third dimension. If I put X, that means inside. If I put dot, that means outside. Like treasure map. If I have a treasure map, okay, they put like this, then X. What do I mean by X? Dig inside. And on the same map, okay, they put what? Circles like this, that this is a mountain, and this dot means the highest point of what? Of the mountain. That means it's out of the page, okay? So again, when I put X, that means into the page. When I put dot, that means out of the page. In our question here, this is the first finger from north to south. This is the thumb going up, so it's going out of the page. So that means this dot represents the direction of the current, which is what? Out of the page. How did I know that? By using, again, Fleming's right-hand rule. What Fleming's right-hand rule states? It states that the first finger represents the magnetic field, the thumb represent the motion. The product, the result of this, is the direction of the current, which will be used by what? Second finger. So the second it will be what? The current. As you can see, I did this in purpose. F with F, M with M, C with C. Okay, let's repeat it with another example. Okay, now I'll try to draw here a question with 2-dimension and 3-dimension. Same question, 2-dimension and 3-dimension. I want from you to try to use your right-hand rule to give me what? The answer, in which direction is the current. But I will give you a hint. If this is the wire, it's perpendicular into the page, that means the current never be to the right or to the left. It will be into the page or out of the page, like this one. If I have a wire like this, that means the current, it will be to the right or to the left. The current can't be up or down because this is the path of the wire, okay? The wire, the current will be inside the wire, okay? Let me try to draw this one, okay? What do we have? We have X. What do I mean by X? Into the page or out of the page? What do I mean by X? Into the page or out of the page? Exactly, into the page. Bravo, thank you. Into the page. X means into the page, dot means out of the page, okay? And we have a wire, and this wire, this is the wire, okay? It's moving to where? To the right. This is the direction of the motion of the wire. That means the answer, the current will be up, the induced current, it will be up or down because this is how it looks, the wire, it's vertical wire. Yalla, if you please use your right hand rule, put the first finger into the screen, into the page, put the thumb to the right. Where's your second finger? In which direction is the second finger? Yalla, tell me. In which direction? Again, first finger into the page because it's X. Okay, that means this X. This X, the magnetic field, into the page. And this is the wire is moving to the right. That means the current, it will be up or down. Yeah, the current, use your right hand. The first finger is into the screen. The thumb is going to the right. Where the second finger? Exactly, it's going up. Bravo. So this is the direction of the induced current. It's going where? Up. This is the current. It's going where? It's going up. It's not out. It's not out. It's up. Marwan, the wire is like this. There's two choices for the current, up or down. How can I get the answer? I'll use my right hand. First finger, right, not left. First finger into the page, okay, because there is X. This is the magnetic field. That means that we have a magnetic field behind me, the north, and behind the screen is what is the south. And the magnetic field lines is going to the screen, okay? And the wire is going where? The motion of the wire is going to the right. In which direction is my second finger? It will be ما بقدر أعمل هيك ما بقدر أعمل هيك لازم هيك يكون in this way, not in this way. Okay, so in which direction is the current? Is up. Okay, but this picture is what? Two-dimensional picture. I will try to draw it as three-dimensional picture. Okay, look here. We have a magnet. Oh, sorry, let's draw the wire first. This is the wire. This is the wire. And this wire is moving where? Into the magnet, okay? To the right, okay? We have a magnet here. I'm going to draw it. Yes, this is a horseshoe magnet. And this is the north. And this is the south. And the wire, as I told you, is moving to where? Is moving to the right or into the horseshoe magnet. Again, you are talking about three dimensions. This is the first finger from north to south. Now, north, it's obvious, is closer, and the south is farther. That's why I put it into the page. The thumb, the wire is moving into the inside the horseshoe to the right. Where's the direction of the current? Exactly, it's upward. So this one and this one is the same example, but two-dimension, three what dimension. This is the direction of the induced what? Induced current. Okay, good. Any question? Any question here? Okay, that's it for today. Next time we're going to explain the AC generator. How does it work? If you have any question, you can stay online. If you